So yeah, so we are moving to data generation and diffusion models. And my goal, so the first part is to introduce you, well, two models, the variational autoencoders and the diffusion model, the basics on it to understand why we go on that way to design data generation models. And then you will have a specific presentation on application, medical application, etc. Okay. So just to clearly understand what we mean by generative model. So now you're specialists, of this kind of application, designing of application. So this is the traditional artificial intelligence. You have an image, you will create your architecture. So here it's a CNN. It will provide you as output a segmentation. So input an image, output the thing you want, the additive value, for example, here the segmentation. The generative model is not that. The generative model is that we will learn something, okay? And so this is with the interrogative point. And when we will be able to learn this, then we will sample from this space. And by sampling on this space, we will know how to transform the sample point to the targeted output. For example, here, a CT for the lung. And so you will create fake images, okay, for each sample. But it should follow a targeted distribution that you want it to learn, okay? So this is what we name by generative AI. So the key challenges when you speak about generative AI is the generative ability. You have the real image from which you will learn your sampling space, I would say. And you will create synthetic images that should follow nicely, perfectly your input distribution. You should not be able to say if it comes from AI or not. You have the conditioning, meaning that when you will sample, you will say, yeah, I'm sampling, but I want at the end to have a panda, an elephant, or an apple. Okay, so you condition your distribution. And the multimodality, I already speak about it just before. For instance, you want to generate an image based on text. So that will be multimodality. So for the generative ability, what you have to understand is that we want to learn to reproduce sample from a real distribution that is very complex and too hard to model in terms of analytics, okay? For instance, in this example, this is the face of human people, okay? So, well, this simple figure is just to show that it's a complex distribution, even if it's only a three Gaussian distribution that I had to create this figure, but anyway. So we will learn a space, a sampling space. So this is this interrogative dot that will allow then, if you sample here, to create synthetic images that will perfectly fit your real distribution. Oh yeah, oops. The conditioning is by the time that you samples, at the sample level, you will say, I'm sampling, but I want to have an image of class 1, 2, or 3. So you will explicitly say which class you want to generate, starting from the same sampling space. And for the multimodality, there's exists so many applications. I know Midjourney, so I speak about Midjourney, but of course, maybe it's quite old now, and there's so many others that happens. I nothing to deal with Midjourney. But, 1 or 2 years ago, I played a lot with it, and I was so impressed by the link and the capacity of the generator to catch some let's say, subjective information that was given in the prompt and to retrieve this image. And this is perfect to illustrate multimodality. Of course, one of the key the last month or year was to do the same, but for video generation. And in terms of energy consumption, this is a nightmare. So don't do that for fun because for the planet, it's a disaster. Okay, there's a lot of family of networks when you speak about generative AI. Classically, we say they are the variational autoencoders. So one that I'm going to speak today. The generative adversarial network that was kind of improvement of variational autoencoders, and the diffusion model that are the ones that are used in the best model right now, like Midjourney or whatever. But all, they have the same idea to say that we learn a sampling space, we sample from it, we learn the transformation from your point in the sampling space to the targeted distribution. It should generate an image that follow perfectly the targeted distribution. So I will start with the easiest to understand variational autoencoders, but don't worry, this is a key point for diffusion models. So it's nice to start with it. So variational autoencoders, the idea is to project the data into a lower dimensional space. So as for UNet, the first part is the image encoder. So you see this encoding wheeling is everywhere, okay? The interest is that the idea is to say, I have complex information. When I force to project it, I will project in a lower dimensional space where I focus the useful information. And that's why it's so powerful. So each image, okay, so you have a data set, you take one image, you will learn a projection, it will be one vector in your final space. So one vector model like that is one image, okay? And so one vector, if I display it in a three-dimensional space, is 1 point. So one image corresponds 1 point in your targeted space, okay? And of course, K, which is the dimension of your vector, is lower than N multiplied by M, which is the size of your image. And so, as I said, the interest is to compact and maybe also interpret representation, but I think this I will not have the time to discuss about it. By the time that you have project your information in a very efficient space, of course, the idea is to be able to, starting back to this point, so okay, you start from one image, you learn a projection to have one vector in this domain, which corresponds to 1 point. Then this point, you want to learn the reconstruction so it can correspond to your input image, okay? So 1 point in this space, starting from it, you should be able, thanks to a nice reconstruction step, to reconstruct an image of a face of a human, okay? And so this is the key to learn this space, okay? So the classical way to do when you have an autoencoder, so I'm not speaking about variational, only autoencoders. Actually, it's very simple. It's like a UNet, in fact. You remove the skip connection and you have it. Okay, so you have your encoder. Okay, here, this is CNN. Okay, so you concentrate your information. You start from an image. Here, you have the decoder of the UNet. You reconstruct the image. Since you know the input image, you have your reconstructed images, and your loss is that your two images should fit. Okay, so it's very easy to learn. So you replace the prediction of your image by, I start with the image, I encode it, I decode it, and the result of this should be very close to my input image. So you don't need any annotation. It's unsupervised. Okay, so it's very easy to do. If you do that, so well, it's the classical way to easily understand autoencoders. Let's start with the MNIST dataset, the very famous MNIST dataset. So this is a dataset of N-craft figures, numbers, okay, 0, 1, etc., that have been done by humans, okay. And so this is small images, and so we will encode them. So we can, for illustration, encode in a dimension of 2, okay? And the big interest of that is that you can directly visualize the learn space, because 1 point, one figure is one color. And since your vector that you learn is a 2-dimension, you display the first and second component, and you have access to the space, and you see how the space is structured, okay? And so you take a 0, you encode, you decode, it should be the same 0. You do that for all the numbers, okay? At the end, you will have that. So what can we see is that things are more or less concentrated, more or less. We can see that numbers are mostly on the same part of the space, which is great because all the 0 should be quite close. So It makes sense that they are projected more or less at the same place, okay? But there's no control on this. It's just we observe it, okay? And what we observe is that there are things that are not so great. First things, the lack of global completeness, meaning that potentially one numbers could be spread on a large part of your space. You don't know, okay? And another point that is not as good as we want is that there's a lack of local continuity. There are holes. And what if I take a point here and I decode it? I have no idea if the numbers I will get at the end will looks like a real number. Okay, so this is two things with which we want to fight, and that's why we propose variational autoencoders. Just to illustrate you, I've learned a space, and randomly I sample my 2D dimensional space with this three points. I use the decoder I learn, and this is the result I obtain. So you see, because of this lack of local continuity and completeness, I have no guarantee that what I'm going to reconstruct looks like a real number, and so this is something I don't like. So the starting point for variational autoencoders is to say, okay, I have a complex distribution, and this complex distribution, I want to replace it by a controlled distribution. And the best one that everyone likes is Gaussian distribution. Okay, so the idea is to say, I want to project everything from my complex distribution to a controlled distribution. Okay, and the name of this control distribution is latent distribution. Latent is a keyword, so you will see it everywhere. How to do that? This is great because mathematician knows that by heart from a long time, far before deep learning, okay? And the great idea was to say, everything that we know, we'll try to apply it to variational autoencoders, okay? So how to do that? If you want to go from this complex distribution to this Gaussian distribution, you have to learn the posterior distribution P of Z knowing X, okay? You have a point here, this one. You want to know its representation in the latent space. You want to learn probability of Z knowing X. So this is to go from this direction to this direction, and to go on the inverse direction, you want to learn the likelihood distribution. You know one point in the latent space, how to retrieve the corresponding point X in the complex distribution. So you see Bayesian formulation is just perfect to what we want to do. Okay, so we will go on Bayesian framework. You can tell me, yeah, but why do you want to express your complex distribution to this control distribution? Of course, is to fight against completeness and locality. Okay, fine. Lack of continuity, of local continuity. If you compress everything on the Gaussian, you will be able to fight with that. So there will be strong assumption that will be done. The latent distribution is assumed to be a normal distribution. There has been a lot of paper doing something else, but what is commonly done is the normal distribution. The likelihood P of X knowing Z is assumed, and the posterior also P of Z knowing X are both assumed to be approximated by Gaussian distribution, whose parameters are modeled by function that has to be guessed, that has to be determined, okay? And that will be the key for this framework, okay? So everything should be represented by Gaussian or normal distribution. And so, thanks. So I'm not entering details, and you can find it. Even if you go on my web page, there's all the mathematical formulation. I don't have time to go there. But what you have to keep in mind is because you're going from a complex distribution to a control distribution with a dimensionality that decreases, you will model your posterior distribution by an encoder, so a simple CNN, that you take an image as input, and as a guess, it will, as output, it will guess the mean and the standard deviation of the posterior distribution, whose assumption is a Gaussian distribution. And to go the likelihood to go from the latent distribution to the data distribution, this is a decoder that you will learn. And the only parameters, because there are assumptions that you will learn, is the mean value. And so for this, you will have a network, and for this, you will have a network. And so basically, this is the loss that you're going to design. You have your image. You want to learn the posterior, okay? That will give you mu x and sigma x. It will allow you to sample a point in your prior distribution, which is a normal distribution. And for the decoder, you will learn mu z to have your decoded images. And this is the loss that you're going to minimize. This part is a data attachment. So you sample a Z, FZ allows you to have the predicted images, and you want it to be as close as possible as the input. And thanks to the formulation, I didn't go into details. You also have a KL divergence. So KL divergence is a tool that allows to measure the closeness of two distributions. Okay, and the two distributions that are under consideration is the prior here, which is the normal distribution. Okay, and here this is the distribution modeled by your posterior, which should be a Gaussian distribution with mean and variance that are guess. Okay. So by doing so, if we retrain based on MNIST, now you have this. If you have a look at the space, and you see that it's more compact, there are less holes in your space, and so you can expect that if you sample here a point, you will decode something that will look closer to a real number. Okay. So you see, this is what you have to keep in mind in variational autoencoders. We want to better deal with the structure of the latent space. So we impose soft constraint to impose the global structure of the latent space. And there are so many works on that in medical application. I don't have the time to discuss, but this is key for medical application. And for instance, so it's very funny to see that. So you learn your variational autoencoders. Okay, that's it. Now you start from the latent space. You take 2 points, one corresponding to a 0 and one corresponding to a 7. You do a linear interpolation in the latent space. And for each point that is in this line, you use the decoder to reconstruct the image, and you see how it goes. Okay? So you see the continuity. It illustrates the continuities. So you can say, okay, cool, that's it, end of the story, thank you, bye-bye. No, it's not so easy. Why it's not so easy? It's because of this. In fact, when we minimize, when we learn our variational autoencoders, there is this KL that say the two distributions should not be too far. So that means that the output of your posterior should not be too far from a normal distribution. But this is not a strict constraint. This is a soft constraint. So you have no guarantee that if you sample a point, it will correspond to your distribution because of this soft aspect of the minimization. Okay? So this is exactly what I say here. These two distributions should remain close, but there are no guarantee that they are perfectly fitted. And so no guarantee that when you sample from your space, you will reconstruct an image that nicely fits your targeted distribution. Okay? And this is the idea of diffusion model, is how to impose a hard constraint between the link between the complex distribution and your control distribution. How to do that? So how to impose hard constraint to ensure a direct transformation from the latent space to the target distribution. The idea, well, so the modeling is definitely more difficult than variational autoencoders. This is based on Markov chain rules, for those who knows, whatever. The basic idea is to say I have a complex distribution. So for instance, the image of CT thoracic human. So each point corresponds to my image in my illustration. And what I want is that step by step, I want to put noise inside this image. So you can find this quite strange to do that. But the idea is that step by step, we will go up to an image of the same size where each value of this image comes from a normal distribution. Okay, and so this is a way, because of course, if we learn that, then we will learn the inverse transform. But if you are able to do that, that means that at the end, you will be able to sample each point of your image following a normal distribution. Okay, so this is the interrogative point in my illustration at the beginning. And you will see that effectively, by applying the inverse transform, you will retrieve an image that perfectly follows the targeted distribution. So that's why we go to this noisy image. If you do the parallel with VIA, that means that you want to learn several steps that allows to go from this image to this space, but with a hard constraint. Okay, and then the reverse will tell you how to go from this to this, and this is a diffusion model. And so the theory behind that is based on Markov chain rules. Okay, so the idea is to say, I have an image, I had small noise, I have another image, I add other small noise, etc., up to the end, and thanks to the equation, I will show that at the end, all the pixels follow a normal distribution. And for the reverse process, I take randomly generated images with this distribution for noise for each pixels. I will apply the inverse transform step by step, and at the end, I will retrieve an image that perfectly follows my complex distribution. This is diffusion model. It works like that. Just with small equation, but you will see it's not, well, the basics are not so hard to understand. How to guarantee that by doing this process, at the end, I will have for each pixel this normal distribution. The idea is to go from this state of my noisy image to this state, okay? We will apply this equation. So this equation is what? So it models the probability of having xt knowing xt minus 1. And this equation should follow a normal distribution with this as mean and this as variance. Okay, and beta t is a law that you will see that is in pose. So that's it. To go from this image to this image, we had a random noise that perfectly follow a normal distribution, okay, epsilon t. Why I'm speaking about that? Because if you want to express this, you can also express it like that, okay? And it makes appear this epsilon t will be key for the rest. So epsilon t in this equation come from this equation. Epsilon t correspond to a pure noise, normal noise, sorry, for each pixel, epsilon t, okay? So if we apply this process, just have a look for the extreme case of beta t. If beta t equals 0, okay, if you put 0 here, you will see that the probability of having xt knowing xt minus 1 is exactly equal to xt minus 1. So your image do not change. So you see it's at the beginning. If beta t is very small, that means that you will keep the same image, but with a small amount of, or even 0 amount of noise. And at the far end, if beta t is equal to 1 and you replace it in this equation, you will have that the probability of having xt knowing xt minus 1 is a pure normal distribution. And this is where we want to go. So by playing with beta t, we can say we stay at the complex distribution, or we go to a perfect normal distribution. And so that's why in the classical method, people use a linear variation of beta t from 0 to 1. With and here in the abscissa direction, this is the number of iteration to go from this to this. Okay? So at the beginning of the process, beta t is almost 0. At the end, it's almost 1. And so this is a way to ensure that you will effectively have this distribution at the end. Because you're using Gaussian distribution everywhere, you can do simplification that are key for diffusion models. So that's why Gaussian distribution are very important. There are work on using over distribution with over property, but the standard way of doing is using a random Gaussian distribution. If you use Gaussian distribution and you express the application of the law from x0 to x1 to x2 to blah, 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 up to xt, you can show that you can directly obtain this noisy image that has been obtained by a process of adding several noise directly from x0, that is here, using this equation. And this equation makes appear epsilon t, which is the noise that has been applied from t-1 to t. But if you have this noise and you know the law of beta t, again, beta t, usually it's linear, okay? If you know beta t, you know alpha t, it's 1 minus beta t. Alpha bar t is just the multiplication of all the alpha t, okay? So you can compute it, you can compute it. You can compute it, you have x0, you can compute it. This is the one that you have generated to go from t-1 to t. So you can directly go from x0 to this without the need to do the full process. Okay? And for the reverse, if you go to this image, you generate this image, xt. If you want to estimate the previous image, thanks to all the equation, you can estimate it by this equation. And in this equation, what you need to know is sigma t, and sigma t, it's an assumption, so you will fix it, okay? Xt, you know it. Alpha t, you know it, you can compute it. The only thing that you need to know is epsilon t. If you know epsilon t, that means if you know the epsilon t that you have generated to go to t-1 to t, if you have xt, if you know epsilon t, you can go back to x t-1. So the key, based on this image, is to be able to know epsilon t, to guess epsilon t. If you are able to do that, you can do the reverse process and end of story. And this is the key, because typically, to do that, we will train a unit, a simple unit. Okay, how to do that? You take one image of your distribution, you generate an epsilon t, so you know it. Thanks to this equation, you generate the noisy image. Okay, you put it as input for your unit. You know epsilon t, unit has to guess epsilon t, which I name here epsilon theta, because theta means this is the parameters you have to learn. Okay, so it's easy to create at the end. And you do this for all the t of your process, from t equal 1 to t equal big T. Big T usually is 1,000. It's 1,000 iterations to go up to your normal distribution. So I hope it's clear for everyone, but you see at the end, it's a simple unit. Mid-journée, etc., it's a unit. So you see unit is so important in your discipline. So this is the unit. So this is exactly what I just said, and I think I mostly finished with that. So you randomly select a t value between 1 and 1,000. This is your iterative process. Okay, you have your image. You generate a noisy, a pure noisy image with a normal distribution. You create this image thanks to this equation. Since you know x0, you know t, you can compute alpha t based on your beta t. You know epsilon t, so you can create this image. You have your unit. In this unit, the only thing you have to understand is that t value is projected to have the same dimension as each of the layer at the level of your unit, so you can merge this information so the unit can learn to suppress the noise, whatever the t. Okay? So he has to know which t is into consideration to know the amount of noise he has to remove, because this amount of noise is not the same depending on the iterative process. So this is a simple way to take t into account. And to do that, this is cross attention. So the thing that comes from transformer, this is used to mix the information between the t value and your feature map. And so at the end, you predict the noise that you have generated here, you predict it, so you have a simple L2 norm, and that's it. This is for the cross attention I'm passing, and this is your unit. So what you learn at the end is only this. And see if you have learned your unit that depends on T. Now in inference, so this is my interrogative point at the beginning of my presentation, you randomly sample using for each pixel a normal distribution, okay? And then you apply this iterative process, starting with big T, so 1000. You will estimate the noise that you have to use to denoise the image to go to the next step, etc., 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 up to the end. Just to finish, two slides. This is one of the most powerful tool that is still currently used. It's named LDM for Latent Diffusion Model. And the thing that you have to understand, so you have your diffusion process. This is your unit, the one I just speak about. And the good thing is that at the beginning, to reduce the dimensionality of your problem, you will use a variational autoencoders. So epsilon and D here is an encoder and decoder of a variational autoencoders that are trained before. The weights are frozen, and then you will learn your diffusion process. What is the interest? If you remind what I just said, the variational autoencoders start to express your complex distribution close to a normal distribution. Okay, it's not a hard constraint, it's a soft constraint. But it's a smart way to start to project to something which is close to a normal distribution. Okay, so it starts to do the job, and then, and of course, it decreases the dimensionality of your problem since this is an encoder. And so then you are able to do your diffusion process. And because you express things with cross attention, you can do multimodality because you have the conditioning capacity. You take a text, you encode it using a text encoder with transformer. You will have basic information that you will be able to interact using the cross attention that I display here, and I didn't have the time to express, but you see Q key V. It's exactly what we have done with transformer. Here it's a mix between CNN and transformer. And that's it. Maybe Thomas just said that before going to the next talk, I can answer to some questions.
The two will be quite clear because after, well, I'm going to discuss about the medical application of that, and after Christian is going to go in the generation process. So I have some questions later.
I can ask one. Is it difficult to train? Are there some problem in the diffusion model that you have to take into account when you train it? You want to, you need diverse data. You need what are the requirements to?
Yeah. For definitely, you need diversity of data from the beginning. If you want to learn complex distribution, you need many cases to learn the diversity. Otherwise, so this is something we used to do. We learn a model, we generate fake cases, and I know that there are metrics that will be discussed after that allows to tell you how far are your new generated samples compared to the input image. You will be mostly a perfect fit if you have few samples at the beginning, because the model will just learn to regenerate the samples if there lack of diversity. So if you want to be very able to generate new data that was not inside your input data set, the diversity should be high. Otherwise, he will learn by heart what he has seen. So this is key. Definitely.
So the key is that you have very diverse data.
Yes.
And it should be real data. of course, you could
Well,
not
it's anything. So this is the beauty with that. It's anything. It's the framework is you want to model a complex distribution, whatever the distribution. So it could be images, but it could be vector field. It could be anything, pathology or whatever you want. So yeah. Yeah, this is one difficulty in medical images. But yeah, for applications, Thomas will give you a different example where we succeeded in applying them. So I will not spoil Thomas.
Are there questions?
Thanks for the talk. So regarding the diffusion model, I'm not sure I understood how you do the conditioning. So
yeah, that was the slide I was moving too fast.
Yeah,
for asking the question. I was just not to think about it. Now, so this is the key. So okay, sorry. Oops. So for T, okay, there are cross attention, but I will speak how we do that. But then you can replace your T information, but by any vectors, any token that has been generated. For example, if you have text, you can encode the text into tokens, so vectors. And so what I'm going to tell you, you replace T by your token. So it's generic, what I'm going to say. But here the question was to say how I'm able to give the T information to my unit, so to use only one unit to estimate the amount of noise I have to retrieve, whatever the time in my iterative process, okay? So I need to provide this information, which is not an image. How I do that? The idea here is to learn a projection matrix that allows to express T value to a feature map that has the same size as the one here, the one here, the one here. So it's a basic matrix projection that you learn for each level first, okay? And second, you have, okay, let me see. Yeah, you have your, okay, I don't see. You have your T value, okay? You exploit it, so you learn the projection matrix, so you learn a feature map that has the same size as your input image, okay? And then you will learn the Q key V information. Q, okay, maybe here the drawing is not the best. Okay, no, okay, sorry. I go back, sorry. You have the same dimension of your feature space for your image and your T value. The first thing that is done is that you addition the two. Okay, so you addition your two feature map, one coming from the image, one coming from T. This is what is done here, okay? And from this feature map, then you will learn three different feature map, Q, K, and V, okay? With lower dimension. As for transformer, so you need to learn these three projections. And then you will do, as in transformer, you will do this scalar product, this V value, the multi-head, you learn the merging, and so you will have at the end a feature map with the same size as the input one, but with mixed information. Okay, this is for T. Is it this step? Is it clear? Okay. Now, when you do conditioning, you do not do the adding things. Okay, you have your input image, which will be encoded as Q, and the text encoding token will be projected to create K and V at the same dimension, and then you do the mixing like that, and you have the result at the end. Okay? So really, the key is to create the key K value, Q coming from the image, K and V coming from your conditioning. Okay? And then you make them discuss together thanks to this scalar product, which will create the attention matrix to say, okay, this token of the text should discuss with this part of the image, because when they interact, I maximize my representation, for instance. So this is the way of doing. And this is the way to merge CNN with transformer. And many people are doing that now. The in-context learning I discussed in foundation model, if you remind at the beginning, it's exactly that, what they're doing. Many people are doing that now.
Okay, thanks. It's a bit clear.
I have a more high-level question. I don't get the intuition of why learning a network that learns to, well, which noises, and then you learn a network to denoise at multiple noise levels at multiple time steps, leads to learning the data distribution, and thus leads to sampling new data samples. Why wouldn't the model just learn to reproduce those samples, since we are just making it learn noising, and the act of denoising the images which we were noising? All processes know the model is learning the reverse process, so why would it generate new samples?
So if I understand well, your question is why we apply so many iterations, why not going directly from a noisy image from your input image? Is it
also that, yeah, but in general, why is the task of noising and denoising equals to learning the data distribution?
Okay. Well, okay. So it's key. It's based on Markov chain rules. Okay. First, so as I say, it's more methodological things needs to be taken into account to really nicely understand diffusion model. Here, it's more the intuition. The idea is to say, clearly, this is my target distribution. I want noise because to generate new cases, it's very easy to generate random noise, okay? And to start with that. So this is one aspect. We want to go there because it will be very easy to generate it at the beginning of the generative process to reconstruct the image. So how to go from this complex distribution to this one? That's the key. And if you go directly from this to this, it's quite almost impossible, too difficult. This is the theory. And the theory says if you go it step by step, you will be able to learn it. And this is Markov chain rules that, well, the framework that allows to explain why is based on that. Okay,
Thank you.
Maybe an extra question. So for the variational autoencoder,
yes.
So you have this filter space with, for example, in the case of the missed data set, the different digits, so the 8, the 0, whatever. Is there, like, is it interpretable looking at this filter map? Like, we could have thought that, for example, the 8 and the 0 should be closer in the latent space because they looked closer. They are a round circle shape.
Yeah.
And like looking at this latent space, I couldn't say that. Like 0 is the left and the 8 is somewhere in the middle, right?
It's there, yeah. Sorry, it's not this.
So in between, you have like the 2 and over digits.
Yeah.
Like, what is the interpretability of this kind of figures?
If you want to go to interpretability, you have to do more than that. Okay, and there are things that exist and that are very powerful. It's attribute VAI. Okay, attribute regularization. Attribute regularization. If you type that on the internet, you will see that you just need on the loss to add a new term that will allow you to put more constraint on the structuring of your latent space. And for instance, you will encode what you're going to encode. I have the rotation or the slide. You can express attributes that you directly measure on your images, and you will force them to respect the same order in your latent space. And so directly, I have some slides. I'm not sure that it's here. It will be maybe complicated, but I have. If we discuss after that, I can show you. So you can really constrain some axis of your latent space to be highly correlated with meaningful interpretation of your numbers. And so if you do that, it's not hard to do it. You just had to add a new term. You will better constrain your latent space to make it interpretable. Here, it's too early. It's not sufficient, what I just said. It's a way to better deal with your structure space because you want everything to be compact and close. But still, to go to interpretation, it's not enough. You have to do more. But there's so many things that has been done here to make interpretable the latent space.
All right, thanks.
Just to complete, yesterday, Nicolas Duchâteau presented you an approach like that with a cardiac, where two dimensions are related to the big volume, one to the size of the heart. I don't know if you remember that. It's exactly this idea.
Okay.
No.
Thank you for all of that. I think we have to go on the presentation. So I let Thomas take the floor.
Okay. Oh, so I can use this one. Okay, is it okay like that? Okay, so just a transition between the two talks. Okay, few questions for you. So I expect you are not sleeping. So we are dealing about generating data, but why? Why for medical image it's important to generate realistic and useful data? Have you some idea? I just highlight 3 points. Maybe there is more, but from your point of view, the lacks. Yeah. What for? Why having more data is better? Yep. Okay, it's every time true. If you have more data, your network and its training will be easier. Okay, but this data must be annotated in one times for segmentation, classification, for many applications. It's important to have some annotation of that data. Is it something that is easy to have? For example, for segmentation, is it easy to have a lot of data, a lot of segmented data? Have you experienced that? Going through your team, to your medical team in the hospital and ask for clinicians to manually annotate 10, 20, 50 3D scans? Oh, it's a pity. It's a very huge work. So it's also very interesting to be able to generate data that is also annotated. Okay, and is there other points from your point of view about the interest of generating medical data? Hard in which sense? Yes. The problem is also the cases that are not appearing so often, the rare cases. Yes, it's very important. There is also a big problem for medical data, is the privacy, okay, and the regulatory constraint, okay. We can't do anything with not anonymized data. And just remember that when you have the CT scan of a brain, you have also the face of these people, okay, of your patients. So it's also something that must be regarded, okay, for that thing. So generating data that come from no one can be also very suitable and very important for that's usage. Okay, here it's maybe a summary of that. So we can generate many data, of course. With more data, we better train. There is a cost also. If I would like to take a picture of a cat, I use my smartphone. It's very easy. Look. And I can take 100 or 2,000 of pictures. For an MRI, there is a big cost. And when you are experimenting in your lab, for example, for microscopic acquisition, there is a cost for that. So it's also a good way to think about generating data. Okay, and after, there is also in the title and the objective presented before an ambition that is to produce very realistic data. Okay, but what is realistic data for medical? Okay, we can deal about image texture. Okay, the image provided, generated, should look like very well to the real data. Okay, so according to a given modality, okay, or an acquisition protocol or reconstruction. There is also the problem of the representation of the pathologies. Okay, so you must be able, if you like to simulate a tumor, to create something that looks like this tumor and maybe where this tumor can appear, okay? It's completely abnormal to generate bone tumors inside soft tissues, okay? And there is also the problem of the patient morphology. When you are studying a large cohort of patients, there is many changes of muscle organization, organs organization, and sometimes parts or something like that that completely disturb the global shape, the global organization of your image. The last part to generate data is that this data must be useful. So with the needed annotation, so if you need a manual annotation about, for example, segmentation, it should be done. Actually, we need some link between generating a pure data with a segmented one, and without wrong or biased annotation or anatomies. If you generate something that can look like something correct, okay? But according to the few changes you have made on that, finally your patients change from the healthy classes to the pathologic cases. It's a big problem, okay? We have to masterize that point also. Okay, one problem of this last point, okay, is that sometimes there is no direct application of your generation of data. When you know that later you are going to make a classification or later you are going to make a segmentation, okay, you can assess the quality of your generated data according to the improvement in this context. But you would like also to produce new data in a global way. And for that, if you would like to estimate how realistic are your image, this is a completely subjective point of view. Okay, so how to measure that quality? One thing that has been introduced is the threshold inception distance, said FID, and is dedicated to measure the quality of generated data for diffusion model, for VA, what you want. Okay, here the problem is that I'm going to generate an image, say X, okay? Sorry for, okay, there is a small problem with the screen, okay. But there is no ground truth for that. So in this way, you have to use a statistical point of view, okay? The idea is to compare the distribution of the generated set. You have a reference data set that corresponds to your real image. You are going to generate thousands of images in red, okay? And using an encoder based on inception, this is a quite big network, you are going to extract, you are going to use the last convolutional layer, and you are going to extract the last feature map, okay, and compute for both reference dataset and the generated dataset a normal, the normal distribution according to the first two moments, average and the standard deviation. Okay, as the dimension is big, it's a matrix, of course. Okay, and to compare these two distributions, the idea is that they are completely aligned. Okay. To do this comparison, we are using the 2 Wasserstein distance. Okay. For your next lunch with your family, you can express that it's also a Frobenius norm that is computed like that. The idea is completely to check if globally the deepest extracted feature from this encoder network extract exactly the same thing from the reference dataset and the generated dataset. If it's so, we made the assumption that the image is very close to the reference dataset. So, in fact, this distance must be close to 0, meaning that both sets are the same. Okay, with that, now I will use a lot of slides from Olivier. We can also decompose the generation into 4 different problems. Okay, simply augment the data to improve your network performance, making more denoising, making segmentation, or making anomaly detection. I think no time to deal about all of them. It's not a big trouble. We are just going to focus on some application we can expect. Okay, for data augmentation, one important thing is an important result come from 2022. It's the generation from one of the biggest data sets available, the UK Biobank. They have trained DDPM systems to produce a very big synthesized image dataset. Okay, the LDM used, okay, if we compare the different approach from the VAE GAN, from the least square GAN, okay, this is an example of the real image. As you can see with VAE, sometimes it seems to be blurry, okay. Now there is a way to use also an adversarial loss to limit this effect. But with LDM, as you can see, the results are very close visually to the real images. And what you can see with the FID is that finally the LDM produce very, very small value. So meaning that the image better look like to the real image. Okay, according to test, they apply a classical algorithm to measure the thickness of the brain and compare to basic knowledge from clinicians, knowing that according to the age, you have an evolution of these volumes. In fact, it's quite correlated, but as you can see, there is a kind of bias. Okay, so it's not completely perfect, but this image looks like quite good. Okay, going deeper in the data augmentation, pure data augmentation, we also have made an experiment. Are we able to make a ChatGPT or a DAL-E or a Midjourney dedicated to MRI images? Our idea was to use a very common publicly available data sets. We have segmented the brain structure of these data sets and create legends. So we have extracted from the segmentation some values, and we have generated text legend of this image. Olivier expressed in this talk the way of working with PubMed. We have done it directly from image and from segmentation. Okay, the idea was to use now LDM using this legend and this image to produce very realistic MRI image. It's what we obtain. So if now you enter this prompt, you will get such image, very quite realistic. What is interesting, if you just change one word, designing the MRI sequence, okay, here it's a T1 weighting image, so it's like that. And we just change it to a T2, and exactly we are quite happy because the network has correctly learned to go from a T1 to a T2, respecting the same anatomy. Okay, we also do that for auto image. The FID is not so small, but it's interesting results. Okay, for segmentation, we can augment the data for segmentation in a classical way. Classically, you have your segmentation, for example. You can make some elastic deformation. You deform randomly your segmentation. You obtain something like that. What is also interesting now is to produce an image that is very realistic. Classical GAN or context GAN here can be used for that. It's going to produce from a segmentation a realistic image. What has been done in this work that is interesting is that dedicated feature values has been coded for each muscle here. In fact, it's exactly as coding a kind of latent space in order to produce different tissues signature in the reconstructed image. So here you finally obtain such result from the no deformation data set, and using the deformed one, you have that. Okay. If you look closer, the image are perfect in accordance to the pathology that wants to be mimicked. But if you look at the femur, here, the bones, the shape is not correct. The elastic deformation augments your data set, but not produce very probable data. Okay, so it's why DDPM for us, it's a very promising way, because with such approach, we might be able to preserve the anatomy. What we have done is not necessary to go completely to the full noise, to the full Gaussian noise. To stop a little bit before, to be sure to preserve the input anatomy. Our cases was to integrate metastasis lesion in this femur. We don't have a lot of data to do that, and segmenting manually this lesion is very, very hard, even for experts. Very discriminating true lesion and false lesion is very hard, okay? So from our data set, we have a very small amount of true lesions. We don't have a lot of healthy femurs, but it's more easy to obtain that. And we have also experts that draw some lesions, and they are not well agreed with each other. But finally, if we like to generate some lesion, it's quite easy. Finally, we can set a seed somewhere in the femur, grow it randomly. Of course, it's not completely randomly. It's based on assumption about the materials. Okay, so in fact, the growing is a little bit constrained. And then we are going to pass in this area something that is look like real intensities from lesions. But as you can see, it's not completely realistic. Okay, and it's why then we are going to use DDPM to obtain a very nice image. According to what explained Olivier, we can change different parameters of the DDPM. And if we have selected the lambda is equal to 20, it's a way to jump to a given amount of noise. And from this image here, the image is very realistic. What is very interesting is that we have set the position of exactly the shape of the lesion. So we know where it is. So in fact, we also have the mask of that. And we have proved that with using that augmented data set, we can generate 2 sons of data. If you simply use the real case, your segmentation is very bad, okay? A dot for 45 of dice is ugly, it can't be applied, okay? If you train only on synthetics, or in fact, without any DDPM, you a little bit improve, so meaning that more data you have, better the results are. But if you use DDPM, you still improve. And if you apply a small fine-tuning on the 29 real cases, you still improve it a little bit. Just to show that this problem is quite hard, the interoperator variability for the dice is 0.7. So in fact, meaning that there is a lot of difference between 2 expert segmentation. Okay, there is many other applications, but I prefer to switch to Christian that will go in details to the generation of the data. That's it? Yeah, maybe just.
Okay. Maybe we could ask 1 or 2 questions to Thomas, if there are questions. So do not hesitate.
Thank you for the talk. So in the last example you have shown, you still have this manual step where you need to have this mask, binary mask of the defect you want to create on your bone. And you need to place it manually, right? To fit on the bone.
In fact, you can decide on draw what you want in the bone, but what we have proposed to generate 6,000 of images to do it randomly.
Okay, so you just copy and paste defect
You select
on
the
the
seed.
image, and it could be out of the bone?
No, not because we have previously segmented the femur. It's not a hard task in a CT
Okay.
image. And for sure, then you know where are the boundary of your bones. So your seed must be inside your bones, and you can't grow outside the bone, for example.
Okay. That was my question, how to automatize this first step.
Sorry.
That was my question, how to automatize the first step.
It is.
And maybe, so you also need to have this initial binary mask of the defect you want to create. What if this binary mask is not realistic? Like I know for a tumor or whatever, you should have some round shape.
Yep.
If you just draw like a scratch.
It's a good question. In fact, we have applied this to both tumors for vertebrae and femurs, and also for multiple sclerosis in MRI. And for both of them, the shape of the lesions are completely different. For bones, it's mainly constrained by the bone structure, okay, the cortical structure and so on. For the brains, it's more complicated. And it's where you need to have some assumptions on how the pathology can evolve, on which system it is based on. Okay, so for example, for multiple sclerosis lesions, we know that the inflammation is localized in the gray matter, in the white matter. So we know that we can grow obviously isotropically, but if we reach liquid, CSF, for example, or gray matter, we have to stop for that. So it's in fact, to be very realistic according to the shape, it's the clinical and medical exchange that allow you to correctly program the correct assumptions.
Okay, thanks.
Other questions? A small question? No? Okay, thank you again, Thomas. Okay, so I give the floor to Christian.
Okay, thanks again. I'm very happy to speak here, and I will follow up a bit on the talks before. So I will talk a bit also about diffusion models from another perspective, and about another recent generative modeling technique, which is called flow matching. So to the outline, I will give some introduction into this flow matching algorithm, then recap some of the diffusion model terminology, and then we will see also that there is a strong relationship between flow matching and diffusion. So we have two different generative models that are really similar. Afterwards, I will talk a bit about applications, also to the medical imaging domain, because for now we had the applications that was more about data augmentation. But another big problem is if we go more to the data acquisition process. For example, in an MRI, if we want patients to lay less long in this MRI, we can also do some undersampling and then use some inverse problem techniques to still get good images. So here we will look at three different use cases. So I will start with a short recap. So what is the goal of generative modeling? So we want to be in an easy to sample distribution, like a Gaussian distribution. And then the goal is to have some data distribution we want to sample new data points of. And in one step, this is usually a bit difficult. That's how also Olivier already talked about. Usually we take some curve. So we don't go directly in one step. We start with some simple distribution. We have some curve that changes for some small time step only a little bit. And at the end, then we get to some complicated data distribution. So the idea of flow matching is that if we want to have this curve of probability distributions, what we do is we move points. So we start with some Gaussian distribution here, and we move points so that at the end we are at our target distribution. And how does one move points the easiest way? The easiest way is to learn a vector field. So a vector field just tells you at some point in space and time in which direction should our particle move. So to recap, we have some source distribution, which will be always a Gaussian in our case. And we have some data distribution, and we assume that we have samples given so that we can train on them. And then for this flow matching algorithm, we want to find a vector field that drives the curve. So for example, here we would start with some point here. The vector field would tell us how we go along a curve in space to some data point. And the data points will be images. It could be this MNIST images that were already discussed. It could be some MRI images or any other kind of images. And let's say we have learned this vector field, and we will see later how. Then we would get a new data point by just solving this ODE. So we start with a Gaussian sample. We simulate the ODE from 0 to 1, and then we have a meaningful point. So of course, the question is, how do we find this vector field? This is the main problem here. And to start with, let's say we have the easiest data distribution you can have. The easiest data distribution is just 1 point. If we want to go from this Gaussian distribution to 1 point, what do? We just take straight lines. So we take straight lines. We have here some Gaussian point, and then we take this linear interpolation that we can just write like this. And then the vector field would be just, we are at some point and we're looking with this vector in this direction. So this is exactly this. We have x1, the point where we go to, and we distract this. We have to rescale for the time. So with 1 data point, we can easily do it. So then the next question is, okay, 2 data points. If we have 2 data points, then for every point here, we have 2 kind of different trajectories that can cross. So one is if we just take this line and then we go back according to the t here, and the other one is then somewhere else. And then the question is, okay, how would we find a vector field that just goes to 2 data points? And the first idea is we can just average them. Okay, we can do this, and we will see it totally fails. So this is not a good idea. And one can easily see this if we average these velocities, then we can write them like this. We can also write it like this, so it just goes to the average. This does not work. So the main idea of flow matching then is the following. We do not just average them. So first, what we do, we are at some point x, and we want to find a vector field. So first, we compute the x0. We can do this by just using this formula. So we can just write this like this. And then why are we interested in this x0? Because this x0 is a Gaussian point, and for Gaussian points, we have this probability. So what we do is we compute the Gaussian probability of the source point here. And then what we do, we just take the these two velocities and weight them by these probabilities. And then we go directly to our 2 points. So you can see here, so the color tells us how strong the vector field is. If we follow 1 point, it's always that has kind of the same strength. But of course, the more time goes by, if you are here, we would have to go very fast, so it gets stronger. So to give you some intuition why this strategy works. So let's say we are at t equals 0.4. That means this part here should be 0.4 of the whole trajectory. And then we take this point, we get this x0 here. And since we have a Gaussian here, if we are outside, the probability is really low. So we get here a really low value. And here we are closer to the middle of the Gaussian, so we get a higher value. And even if for the unweighted one, this one is a much bigger vector, if we weight this vector is really almost 0. So we just go really in the direction of the target point. And the same is if our time goes higher, it's even stronger, because if the time goes higher, we can see we go so far away from the Gaussian that we really have 0 weighting here. So this is kind of the intuition why, if we take this weighting, we always go to our target points. So this was a bit of math, but I try to keep it low. So if we have 2 points, we just weight them. If we have n points, we also weight them, just with more weights. And if we have a whole distribution, we take some integral. So at the end, what flow matching does is we have a very easy vector field if you have one target point. If we have a distribution of target points, we just compute some integral here, and then we are guaranteed to go to our target distribution. And this is also, so there was a question before, why don't we just go to our target points? Of course, if you only have finite points and we perfectly learn, we just get to our target points. But if we have enough points, the idea is that if we learn, we generalize a bit. So we don't directly perfectly approximate everything. So this was just, okay, how do we mathematically get to this velocity? But if you want to learn this in practice, luckily it's super easy. So we just have to minimize this kind of loss. And in the next slide, we will see the exact algorithm. So what one takes some data points that one has given, the x1, and then one randomly samples a batch of noise vectors and a batch of time steps. So just 3 things we can easily sample this we have given. Then we compute this kind of noised term. So it's a linear interpolation between noise and your data, which is very similar to the diffusion model where you also have this kind of interpolation. We compute here just the difference between our target and the noise. So we have this loss. So we take the velocity. Here we have the xt we computed. Here we have this kind of difference, and then we train with this. And this is all. So you can write this really in one small page of code, and then you already can train these flow models. Yeah, let's say we have trained this. What we do, we start with some Gaussian point. We solve this ODE, and at the end, if we would have trained on some cat pictures, we would have gotten a cat. Okay. So to relate this more to diffusion models that we saw before, we can reinterpret all of what we did a bit. So if you look at this UT, you recall we have had this easy kind of vector field for 1 point, and then we integrate it. What we can then do is we just write this out. So this one we can put in front of the integrals. Here we have x1 and this into here. And here if something doesn't depend on x1, so it's the probability measure is just 1. So we can write
Okay, perfect. Is there some question during this this break, random break, without diffusion break? It's okay. See the links between the talks of this morning?
So just to recap, perhaps, so this flow matching came up, I think, 2 or 3 years after diffusion. The performance is really similar, and we will see also that if one has trained a diffusion model, one can go to a flow matching model and the other way. And this is what the idea now is. So if we say, okay, we just have we rewrite it, and then we have here this integral, how you should interpret this is like the following. So mathematically, even if you don't know what it is, doesn't matter. So what we do is we start at some partly noised point, and then we try to predict what is the clean image. This is exactly what this does. So it is a denoiser. So we start with a noised image with some given noise level depending on t. And then we have a denoiser. And if you remember the diffusion thing, it was very much the same. We have some noise point, and at the end, kind of we want to have some denoise thing. Okay, so if we have a flow model, let's say we have trained this, we can also define then this denoiser by just using this equation. So how would it look like if we are here at a point xt? Then we have some vector that we learned in this direction. If you would take the one-step approach from here, we would go to some kind of image which has no noise, but it's not really a good image. This would be the denoiser, but we just go the trajectory, and at every point we go kind of closer to our denoised image. So at the end, the denoiser should really be the identity. Okay. What we saw before is this diffusion models here, and there the idea was to predict the noise. And you have some identity between the denoiser that we learned here, and here this description of this DDPM scheme. So we see that both of these algorithms basically do the same. They both describe clean data from some noised image, but how can we make this more precise? And there is here some theory about denoising models, diffusion denoising models, how to interpret them a bit differently. If you recall what we had some data point, and then we always added some noise. Mathematically, one can model this as a stochastic differential equation. You do not need to know what this is. Basically, what it says is we start, so if we have some point xt, let's say we would have this noisy dog, we add some random noise in each step. So this is the random noise of Gaussian, depending on the time step. And this one here just makes that the norm of the image doesn't explode. So basically, we can describe this noising process also differently. And now the interesting part is that we know how to go back theoretically in the STE theory. Also here, you don't need to know how this mathematically works. But if you want to go back, so we want to go from here to here, we basically have the same equation. The only difference is we have here some gradient of the probability at t. So in the reverse step, we just have to kind of use this. And in the diffusion models where we look at this kind of score, so this is called a score, we learn at the end this quantity. And then now you could say, okay, this looks so complicated. Why do we do this mathematical things? At the end, if we want to learn inverse problems, then the probabilities are really important. There we will really use this score. Okay, so to make some connection to the talk before, this DDPM noise prediction here is really similar to the score modulo some scala, depends on the time. And this is kind of the so one of the main things I want to make sure that you get is that basically flow matching and diffusion, they are really similar, and we have some affine transformation. So here we have some this flow matching. We saw before this flow matching can be written as a denoiser, and then we have here this score formulation from the STE. And then at the end, we have this DDPM form. So they are basically all the same. I say basically all the same because one goes from 0 to 1, the other one goes from t to 0. So we have to be careful a bit about the t's. There's always some rescaling, but this is just some details. So if we have trained the diffusion model, then without doing anything, we get a flow model. So we don't have to always add some noise. We can just solve some ODE. And the other way also, if we train a flow matching model, which is really easy also to train, we can get some diffusion model. To get a bit yeah, so why we do is, this is, we will see later, is because we want to solve inverse problem at the end. Here is some examples. So what you see here is really the path of the STE part. So this would be, we have here this, we start here, then we have to add some XT, and here would be the score that we learned, and we have added some noise. What you see here is the denoiser prediction that we can get exactly from this thing here. And you see that at the very beginning, we have some noise, some Gaussian noise. And the prediction here is just kind of the average of all our images in the data set. So because here we don't have any information. If you go a bit further, then you can see there's already a bit more structure. And if you look here then at this was, I think it's empty perhaps. Yeah. So at T 0.2, you already have kind of a phase, and at T48, you're basically at the final phase. So now what you can do is we start in the same initial noise. So we start the same, you can see the left image is the same. But every time the noise we add, this one, okay. Yeah, thanks. So the noise we add here, this is something stochastic. So every time we draw new samples. And this time we start in the same source point, but the noise here we take is different. And at the end, we get a totally different image. So this really tells you that diffusion is a stochastic sampler. If you start in the same image, you do not, in the same noise sample, you do not always get the same output. If you now take this model, so this kind of denoiser, we can also solve the ODE. So here we have no noise term. So we just solve the ODE. Then we can see that very early on, we kind of already know what the image is. So here it changed from here to here quite a bit. But in this flow matching thing, very early on, we kind of, it's just a bit of details that are done. And here also we have no stochasticity. If we start with the same noise here, we always get the same image. Okay, so the recap here of this more theoretical part was that flow matching is another generative modeling techniques where you can generate really high quality image, where you don't have to solve an STE, or you don't have to do all these noising steps. You just learn a velocity field and have some ODE to solve. The learning is really simple. One has just to use some tool regression loss. That's it. We can write this also as some kind of denoising problem, which then connects it really to flow match to diffusion. So one advantage that I didn't put here on the slide is there's also extensions of flow matching where one can go in 1 or 2 steps, because usually you have to solve an ODE, perhaps you do 128 steps, which is costly, but you can also have some extensions where you really need less and less steps. And you don't have to retrain for this. Okay. Is there so far any question to the kind of more technical part, how this kind of works? Yeah.
Thank you. It's very interesting. Can we say that each step in the denoising process, when we are looking at the diffusion perspective, is like taking a step in the vector field towards the data distribution?
Yes, it's
like the 3D formula you said shows, I don't know, but it shows equivalence to the diffusion perspective versus the flow-based perspective. So is it correct? Just if I'm trying to get the intuition of diffusion model, like each time I denoise, my model denoise the image a bit. It's like taking a step in the, because vector field is much more intuitive, like I think.
Yeah.
The gradient compute.
But basically, so it's true, but already if you go here, kind of I have to take the other one. So if you do this diffusion thing, you have this deterministic push that kind of pushes you to your data manifold or where the real images lie. And then you always have some random noise that kind of deviates your path. But you always have this kind of deterministic push that is very similar to the ODE formulation. Also, if you take this noise, so here I have the square root of 2. You can also have a smaller one, and the smaller you go, you more go to some deterministic trajectory.
And just a same but a separate question is, if my goal is just to generate or learn the data distribution or generate new samples, why would I, is there a preference, should I have a preference to go with flow matching perspective versus diffusion perspective? Are there some practical implication that one is better than the other, or is it same?
So it depends a bit. If you want to train fast and easy, I would say flow matching is really good. Sometimes I think diffusion still is a bit better in terms of FID. If you want to do like few steps sampling, so if you really want to do like 1 or 2 steps sampling, then you should look for mean flow, which is an extension of flow matching. Otherwise, there's also other techniques which we have to retrain. And then it also depends what you want. If you need a likelihood, you can get a likelihood of your data also by enhancing the ODE a bit. And there's also new techniques now that kind of do one-step likelihood prediction. So it really depends on what your requirement is.
Just to follow up to that, so we know, like it was mentioned, Midjourney uses latent diffusion. So is flow matching also being used in, I don't know, production settings to use, or is it more new?
To be honest, I don't know, but I would guess, yeah, because there's no reason why you should not do this latent. I mean, yeah, for sure you can. So there is works where you put something in the latent space and then you do some flow matching there. Yeah, it's definitely doable. Okay. Thanks. So now we change a bit the topic. We go to inverse problems and how can we solve inverse problems using flow or diffusion models. So what is an inverse problem? So basically an inverse problem is the thing here on the left. We have some unknown clean image. So this is the thing, or data. This is the thing we want to recover. We have some operator here that degrades our data, and we might have some noise. So one example is if we have some spectroscopy. So we would have some molecule here. We do some spectroscopy, and then we get here some other data, and we want to recover this data. Another one could be source separation, or some seaflow estimation from some echo data. So we are only interested here in imaging applications, and the easiest one is if we have some linear inverse problems. And in medical imaging, a typical thing is we have some MRI reconstruction. So we have some under-sampled MRI image, and we want to get some image that looks better and is more clinically relevant. Another easy example is if you look at this MNIST numbers we had before, we could just start, okay, the operator A is, we have some number and we want to have the digit. So if you have the digit, we want to reconstruct some number. Or another thing would be in painting. So let's say we have an image, and then we apply a mask. So we mask out here this 2FL. And then we want to reconstruct, then we don't have this 2FL anymore. So this is also kind of an inverse problem. To see what do we really want to get from an inverse problem, we take this easy example of MNIST numbers. So this would be like 10,000 different MNIST numbers would be our data set. If we have then this inverse problem where we degrade our number here, so we would say we go, if you look at the number and it should be 3, then we have some posterior distribution. So the posterior distribution is just the distribution of our numbers, given we know that it is a 3. So this can be here a very kind of big distribution, but we can also be interested only in the most likely number. This is called maximum as posteriori approach. So this is kind of the two things we want to recover, either the posterior distribution, the whole distribution, or just the most likely. So this is kind of classes of inverse problems that one can look at. So if we have the forward, it might be we don't have the forward operator, but we have paired data. So then we can just do it fully data-driven. We just learn from the data how to go from Y to X. We could also have something like we have the forward operator and we have data. Then this is often known under physics-informed neural networks. It might be that we have the forward operator, but we have no paired data. This is something we will also discuss today. And we can, there's also the case where we don't have either. So we just have some observations. We have some clean images, but we don't have some relation. This we will not discuss today. So we'll start with some example where we have paired data. And we want to sample from the posterior distribution. So we don't only want to have one output, we want to have the full distribution. And this can be easily done with flow matching, but a similar thing can be also done with diffusion. So we have some inverse problems, so some operator plus noise is our observation, and we are given a lot of data points. Then what we can do is we just train a flow on the product space. So our flow model now takes as input the observation, and it takes as input kind of some noisy image, and then it should output a vector field. We can take exactly the same loss. The only difference is that we have paired data here, and we put the Y into our vector field. And then if you want to sample, what we do is we start with a noise sample, and then we just solve this ODE while this Y is just fixed. So here the example would be we have some smiley, we do some CT undersampling, and then we would have some trajectory with this vector field. So just to make it in this really simple example, we still have MNIST, and this A just tells us what the number is. We start with some paired data, so we have a 3 and a 3 here. We have a, oh, this should be a 2. So here should be a 2, of course. Otherwise, it's not paired. Then we would sample some noise images and some times. We get some interpolation paths. So here we would have the interpolation of these two images. And then we would take this as the loss. So we take here the 3. This is our observation, this noised image, and then here this vector field we get. And then we have, of course, we have to sample many and then update this. And if we then want to sample from the posterior, the only thing we do is we draw some noisy image here, and we solve this ODE, and then we will get very different, a lot of different tools. So perhaps a more realistic example to see that it also works on more realistic inverse problems. So if we are interested in MRA data, usually what one can measure is some Fourier space data, so the Fourier transform of our X. So here we would have the Smiley. This would be some Fourier transform, but data acquisition in MRI takes time. That's why you're so long in the scanner. So you can't just say, we don't sample all of the data, but just parts of it. Then we can reconstruct. We take the inverse Fourier transform, and you can see we get some artifact that doesn't look so nice. And then the question is, can we then, with this flow matching technique, get back our real image X? So here's some example. So here we would have some ground truth data. So in this time we have paired data. Then we have some undersampled image here. And you can see it really looks blurry. We don't see the edges here clearly. We use this algorithm, and then we see what the outcome is. So here's one sample that we sampled. It looks, I would say, pretty close, of course, but it's not exactly the same. You can see here some structure is not found. Since we can sample a lot of points, we can also look at the mean image. So this would be like the just the mean of this data set. We can see where it differs from the ground truth, but we also have some standard deviation. So here we see that not all the flow samples we generate are the same. We really have some standard deviation, and the standard deviation is also in the areas where it's perhaps something is going on. So on some edges where it's not so clear what should happen. But in general, this is a way to solve inverse problems with these flow methods. So now we will go to another method that also is based on flow. But here we only want to have one sample, so one good sample from our posterior, and we want to kind of get an argmax, the most likely sample. And in this setup, we have a known forward operator, but we do not have paired data. And this is, I would say, where the strength of generative modeling lies, because we can just unconditionally train a generative model on a big data set with no annotation, so with no paired data, and then use this model to kind of solve our inverse problems. We'll do this. How much time do I need? Yeah, and one thing that we will use in the following is Bayes' theorem. We kind of already had it here in the slides. So if we take the probability of x given y, we can always write this as some product here, probability of y given x. We have to multiply here by probability of x and then divide by probability of y. So this is a standard thing, so I won't go into this example. So why is this interesting? So if we want to compute here this argmax probability here, I can use this formula. So first of all, we can take the logarithm. It doesn't change much. Then we use the formula, so we can split it in two parts. There would be another part from the y, but it doesn't matter because we take the min only over x. And we see that we have two terms. So one is kind of the data fit. It tells us, okay, how likely is our approximation, our observation given x, and one is kind of the prior fit that tells us how likely is our data. And this part, this can be then modeled by this generative models. So a typical thing, like a classical thing, how to solve these inverse problems is to have some iterative optimization. So we take some data step. So we take here some gradients on this data term with some step size. And then if we have done this data step, then we look at the prior distribution. So this would be, for example, the distribution of all MRI images, and we would take some step here to make the image look more realistic, and then we could do this iteratively. So a lot of classical algorithms look like this. And something, so one of them is called PNP, plug and play algorithm, and it replaces kind of this step here with some denoiser, with some Gaussian denoiser. And denoiser, we've seen denoisers before in this talk, and this is exactly what it will be. So the idea of this PNP flow paper here was that we know that flow matching basically is training a denoiser. So we can use this denoiser that is defined by the flow matching and directly put this into this plug and play iterations. And in principle, I can do it, but there's one problem. So where is this trained on? We know that this is trained on these XTNs that look like this. So these are noisy images of a given noise level. If you now put some random data point here that does not have the same noise level, our network never has seen this, so it will fail. So this is you cannot do this. So at the end, you need to kind of re-noise your data here to get some meaningful output. So we will see this at some easy inverse problem. So this is some original image. This is from there's some CellLab A. This is celebrity data set that's usually often used in machine learning or generative modeling. We take this image, then we have some mask operator, and then the observation would be we just have parts of the image we don't have given, so it's some inpainting. So how do we derive the data term? So we said, okay, we have here this y, this is this ax, and then we add some Gaussian noise here. Then the likelihood here of a given x is just a Gaussian. And this is just the case because this is deterministic. Here we have a Gaussian, so let's have some Gaussian likelihood. And the data term then we have here, we can explicitly write this data term down. Okay, how does this algorithm work now? So we start with an arbitrary initialization, and then for each time step, we do the following. So first, we do some gradient step. So we go in the direction of our observation. That would be kind of here. Then we have to re-noise because our denoiser or our flow matching algorithm has only seen images of this kind. So we re-noise it. And then we put this into our flow denoiser. And you can see this is kind of similar to the image we had at the beginning. So this is the first iteration. Then we do it another time and another time and a lot of times. And at the end, we get some output that really looks like a realistic image. Although we only have given this into our algorithm. And we never trained the algorithm on some inpainting problem. So the algorithm is just trained on some clean images. And also, of course, this image was not in the data set it was trained on. So it's a new image we take a new mask, and we still get something that looks like this. And yeah. So it works pretty well, but it depends a lot on how good is your flow matching model. And here you can see some other examples where one can do some inpainting, and in general it works pretty well. There's a lot of similar works, and this is really an active field of research where every couple of weeks there's a new kind of algorithm or adoption of these algorithms. So for now, what we had is we had only one image kind of that comes out. So every time we start with a noise, even though we kind of noise in the middle, usually we only get one image. And if we now want to sample from really the whole distribution, we can use this diffusion process. So here we have the same setup. We have a forward operator, but no training data is given. So instead of just taking here some argmin, and then we do some kind of optimization using our model, we will here have this stochastic dynamics from our diffusion model. Okay, how does it work? So let's go back to the unconditional diffusion model. What we had is we start with noise here, and then we know we have some gradient of the log probability at t, and then we go in this direction. If we now want to incorporate our inverse problem, so our y, our observation, what we then would need to do, so this is one can compute this, we just replace here the normal score, so this one, with xt given y. So this means we need to have this property, this object. The problem is the only thing that we have given is here the probability of y given x, so it's the wrong direction. We only have this for our data, so at 0, so 0 is here. Then it's just kind of if you have a linear inverse problem like this. So how do we get this score just using this? So first we use base rules again. So if we have xt given y, we can always write this as xt, and then here we have the other direction. So the good thing is this one we have because this is what our diffusion model learns. This one we still don't have. This is a bit of a problem. But then so the idea of this DPS paper was that instead of computing this term here at time t, and here we have some xt, we take directly our data term at time 0, and here we replace xt by the denoised version. And this is also the interesting thing. So since we know that the score that we learn and the denoiser, we can get one from the other, we can directly compute this quantity. So this is also one of the main drawbacks of this algorithm, is that this approximation is sometimes really bad. So it really depends on your application. So we have the same problem here. So we have this marking compute in the same manner. And now if you look, okay, but then it works. We take this approximation, and this approximation is just some gradient here. The only thing that you should perhaps have in mind is that we have to backpropagate or take the gradient with respect to this network. So this is the network. So if the network is huge, then this backpropagation or this taking the gradient can be a bit heavy. Okay, so how does this DPS algorithm work? So we start with some noise. Here at t equals 0, that is really pure Gaussian noise. And then we take this denoisers step. So we predict a clean image, and at time 0, it's exactly the same image we saw before, because we don't have any information, or not much information. Then we take the standard generation. So what this means is we take here the score that we know we can kind of compute via our denoiser. And now comes the guidance term. So this guidance term, we use exactly here the formula we saw before. And then we apply this guidance step, and then we have something new. And you can see, of course, at time t, with a small step size, we don't see much. If we go to a higher time, so let's say t 0.15, you can see we already are in the right direction. So here we had something very generic, just some kind of face looking like image. But here we see, okay, at least the color is kind of right, and the hair also similar. And if we go for, so okay, and one thing I wanted to note also is if you look here at this gradient step, so this gradient, we don't really see the mask. So at the beginning, it really changes kind of everywhere. But when we are at very high stages, our denoiser is kind of the identity, and that means that here the gradient here, because we have no information, is 0. So here is not much changing anymore. It's more changing on the outside. But you can see that here we get some image that looks kind of pretty good for this inverse problem. We even kind of a bit have this thing here. One should say that the quality of this generation will also depends a lot on how many steps you take. In general, this is more heavy than if you take the flow matching approach, because you have to differentiate here through this network. But the advantage is that if you do the same algorithm with different noises a lot of times, you get a lot of different images that fit your inverse problem. So there's a lot of, from this DPS formulation, there's a lot of applications in the medical world for MRI, undersampling reconstructions, for CTs, also for PET CTs. So this is really an active field of research, using some pre-trained models on some data distribution to solve very different kinds of inverse problems. Okay, this was this. Thanks a lot, and I'm happy to questions.
Thank you very much. We have Little time for questions. No questions?
Yeah, maybe I have a question. So thanks very for this great talk. Every time you speak about flow matching, you go to the noising space. But from what I understood, you're not forced to start with this noising space. You can also model things with another distribution. For instance, you can start with LC subject, which is one distribution. The other targeted distribution is the pathological cases. And so you can learn the flow to go from one to another one. Can you say some few words about this?
Yes, that's totally true. So in this flow matching thing is, it's not, you don't need to start from a Gaussian distribution. So where do we have this loss? So here, so you don't have to start here with Gaussian points, not at all. And also here, I draw this independently. You don't have to draw them independently. You can also do some optimal transport that you pass straight. So there's a lot of design choices. If you don't start with a Gaussian point, or you don't use this independent coupling, then you don't have this relation to your SDE. So you cannot switch from one to the other. But depending on your application, that might be beneficial. What you can also do is that you start as a distribution, and then you have some noise in between, and then you go to your clean target again. So here there is three kind of references. If you look at this Albergo reference, they have kind of a more general approach for this one, where you can start in a distribution noise in the middle and go to your clean target distribution. And this can be beneficial if your distributions are, so if you want to do some distribution matching or so, this might give some advantage. But yeah, there's a lot of design choices here.
Okay, thanks.
Other questions? So I think you are tired. Or maybe you are hungry. Okay, so thank you very much again for all the speakers. So it's time for